Hello, Physics 30s. Welcome back. Hope you guys had a good long weekend. Uh, I want to talk today about half-life, and I'll also touch on fission and fusion. These are the last two concepts in chapter 16, and the math with them isn't really that bad. So let's start with half-life. You may have heard of half-life already. I know some of you, if you've taken Math 30, you've had to calculate it using logarithms. And I definitely want to show you how to do that. But there's just a really practical way to handle the principle of half-life. Now, we've been talking about radiation and why particles or atoms are not stable. And atoms that aren't stable are trying to become stable by undergoing alpha, beta positive, beta negative, and even gamma decay. Now, what's really interesting though is over time, scientists have understood that certain elements or certain isotopes of elements will decay, like will break down into simpler things at certain rates. And statistically, what they've called that process is half-life. And all it is, as it's defined, it's the time for half of the nuclei in a radioactive quantity to decay. How long does it take for half? And so it's often measured in just, well, it can be measured in any unit of time. Like some of the really unstable elements only take milliseconds to decay, or even less. Whereas more stable elements take thousands and thousands of years. Carbon 14 is the video. If you watch the video, it's really, really good on carbon 14, just explains it. Carbon 14 is kind of a benchmark isotope of carbon that's used to determine how old a fossil is. They're good up to like, I think it's like 60 or 70,000 years or something like that, or even more. But when it's expressed, as it says here, carbon 14 has a half-life of 5,730 A. The A is a Greek, or sorry, I think it's Latin, sorry. And A stands for annum or annually, okay? Sometimes I've seen just the designation Y for years, but A is annum, okay? So that's quite a long time. But what that means is for carbon 14, if you had, say, 100 grams of pure carbon 14, let's say you had 100 grams of just carbon 14 only, after 5,730 years, you would have 50 grams of carbon 14. Uh, the other 50 grams would have decayed probably into nitrogen. If you saw in the video, like they decay back to nitrogen. And then anyway, you could wait another um, 5,730 years, like that's an average, right? And then you would have 25 grams, okay? So determining half-life, there's actually three ways to do it. One is just using any tables. If you're given a table and it tells you, how many grams of a substance are left after a certain amount of time. Graphs are pretty straightforward, I'm hoping, as you saw in the video. A graph would look definitely something like this, where you see you'd start with this would be 100% sometimes. Okay, but whatever's on the y-axis, here it's starting out with it looks like milligrams of, this is iodine 131. Okay, so this is an unstable isotope of iodine. Here, move this up here so you can see it. As time progresses, you have less and less of the original sample that is still iodine 131, like it's decayed into something else more stable, okay? But after a certain period of time, we get right to here, okay? Now you're down to 1 milligram, okay? So after a certain amount of time in days, looks like this is days, okay? Sorry, I don't cut that off a little bit. You've cut your sample in half. So then how long did that take? Well, according to the graph, this looks like it's increments of individual days. So it looks like it took 7, okay? So according to the graph, after 7 days, you would have cut your sample in half statistically on average, okay? And then of course, so that means then, hey, if that's happening every 7 days, then if you do 2 half-lives, that would be, oh, did I do that right? Because, yeah, the time in days here, it looks like it went up to 16. Oh, I'm sorry. That's an 8. I misread my graph. That makes more sense. Sorry. Because, yeah, 16 looks like double the half-life. So, sorry, the half-life, I was wrong. I read the graph wrong. See, there you go. That's learning to use a graph. The half-life should have been 8 days, okay? So after 16 days, that would be 2 half-lives, and you would have cut the sample in half again. Now, now we're not cutting 2 in half, now we're cutting 1 in half. So that drops down to a 0.5. You guys can see that there, okay? Okay, so there we cut that in half. And if you were to wait 8 more days, then you would cut that in half, okay? And that would be 0.025. So that would be somewhere in here, right? And then obviously my graph runs out. Okay, so in a practical sense, half-life is seriously just cutting things in half again and again and again, and you get increasingly smaller fractions, but based on that ratio. So I want to show you I want to show you both ways. I want you to know the logarithmic way, and I also want you just to know the practical way. Your formula sheet doesn't have the formula written this way. It actually has it written, maybe I'll write it down here. It has it written like this. It says n is equal to n0 times, or n to the, 1/2. Let me back up here. It's n0, the original amount, times 1/2 to the nth. Okay, and they use little n. Sorry, that looks like an h. They use little tiny or lowercase n as the superscript. Okay, so you can see that there, n is equal to n0 times, you're multiplying it by 1/2, the original amount by half, how many times? Okay, how many times? So n, this little n here, is the number of half-lives, that n right there. Okay, if that makes sense. Okay, so it isn't that bad. But I do want to show you the logarithmic. Now, when I say logarithmic, if you've never heard of that before, that means using powers of 10. It's logarithmic base 10. And the function on your calculator is where it just says log, L-O-G, and then above it, it'd say 10 to the x. Okay, so I'll do them both, really. I'll do them both for you here on this first one, and then I will post answers to the remaining ones. Okay, so there's for question number 2, I'll let you tackle that and see if you understand it, and you can check my work for number 2. But I will do number 1 with you, and I'll do it both ways. Okay, so let's just get into it. This question 1 deals with the half-life of carbon. It's 5,730 years, or annum. We already talked about that. So if a 1-gram sample of a living tree produces a radioactive reading of 0.30 BQ. Now, what I should say here about half-life is be prepared for any kind of units. In fact, units that you might not be familiar of. You can measure half-life as a percent, like you can be using percent. You can use grams. You can use atomic mass units. You can use these BQ. This is it's a measure of activity, or radioactive, the rate of radioactivity. And BQ stands for Becquerel. That's after Henri Becquerel, who he actually determined that uranium salts were releasing something that was causing his photographic plates to be exposed. Okay, anyway, so there might be some weird rate that you're not familiar with, but the units, but all you need to look for is the original amount and then the amount that's left over. So and with carbon-14, they always compare to the original sample, which would be a living sample, because in a living sample, like you and me, we're exchanging our carbon atoms all the time. And plants do that too. And so, the amount of the the ratio is stable. And then when you die, though, then you stop obviously living. And so you're not exchanging your carbon atoms for new ones. Anyway, so this 0.03 BQ, this is going to be our original amount, okay, N0. Okay, let's finish reading the question, though. And that says, then a 1 gram sample of a piece of wood with a radioactivity reading of 0.075 BQ. Okay, again, those try not to get distracted by some weird units if you've never seen them. You just need to recognize there's an original amount and an amount left over. Okay, so it's asking you this must be from a tree that died how long ago? Okay, so basically it's saying how old is this tree? Okay, so to use the formula, and some of you can maybe see it without the formula, but anyway, to use the formula, N is the amount remaining, okay, after decay. We have N0 times 1/2 to the nth, where I'm going to use that one first, okay? So what we need to know is we're actually trying to determine the amount or how old the tree is, okay? And what's really helpful with these both of these variations, okay? If you use the one from your formula sheet, which I just wrote, you can see here that n, this little n, is the same as this ratio right here, t over t 1/2. Okay, maybe I'll write that right here. N is equal to, n is really the ratio of the elapsed time. Maybe I'll write it for you. The time elapsed over the half-life time. Okay, so because it's really, well, and then that would tell you how many half-lives, because n is the number of half-lives, right? So if the elapsed time was twice as long as the half-life time, then you'd have t elapsed over t 1/2 would equal 2, and that would tell you that the number of times you cut the sample in half was 2. You cut it in half twice. Okay. Now I'm kind of leading you a little bit because maybe some of you can see that that's what's going to happen, because the really simple way of handling half-life is look at the original amount, which is 0.03, and then you look at the amount remaining, which is 0.075. And so all you can do is then say, okay, well, in your calculator, you just go 0.3 and you divide that by 2. Okay. When I do that, I get, here we can write it by here, divide that by 2, and that gives you 0.15. Okay, well, I have less than that. I've got 0.075 BQ. That's what I have left. So let's divide that in half again. So divide that in half. Oops. And there it is, 0.075. Okay, so then you look at it like, oh, I divided the original sample by 2. So that means there are 2 half-lives. Okay, and if you look at this, you could easily substitute in the original amount here and the remaining amounts. You could take, because the amount remaining would be 0.075 BQ. And the original amount was this 0.3, if I got that right. Yeah, 0.3 BQ. But that's going to be times 1/2 to the nth. Okay, so just without even doing logarithms or anything, we determined that n has to be 2. Okay, this needs to be 2, because if I multiply 0.3 by 0.5 and I do that twice, then I get 0.075 BQ. So with 2 half-lives, then how old is this tree? Well, 1 half-life would be 5,730. So 2 half-lives would be double that. Okay, 5,730. So yeah, the answer here should be oh yeah, how old is the tree? So this would technically be the elapsed time. Okay, I'm kind of using a bunch of subscripts here, but I think you can follow that. So then the time would be 11,460. Whoa. Years. Sorry, I did not write that well. Now, that is you're not using any logarithmic formulas, okay? So 11,460 years. Now, I'm just going to use the space below and then I'll get rid of it because I want you guys to do number 2. But I want to show you that you could solve this using logarithms, okay? So what we do is we basically take, if we want to know how many half-lives were created, I'm going to come back to this. We're actually trying to solve for little n in this expression right here, okay? So if you are trying to use logarithms, which I'd encourage you to be comfortable doing, because sometimes you're going to get a question where it doesn't come out to a nice, clean, whole number of half-lives, okay? Where the letter n, the little n, this n right here, that n does not equal a whole number sometimes, okay? In fact, most of the time it doesn't, but for most of our questions, actually, it is a whole number, but on occasion, it's not. Now, so what that means is we need to simplify this to solve for n. How do you do that when it's an exponent? Well, the first thing you should do is simplify the right-hand side so that you just have 1/2 n by itself. The reason I'm trying to do that is because I want to use the logarithmic function, but I can't do that when this 0.3, I got a number stuck out in front of it, okay? So the best way to simplify this is divide both sides by 0.3 so that cancels out, okay? So I'm going to do that. And this means that this equals 0.25. Now the unit's canceled, by the way, so it's just a ratio. That has to equal 1/2 to the power, I'm sorry, this is 1/2 to the power of n, okay? Now, here, I'm gonna keep moving this up here. Sorry, I'm just writing over it. Sorry, it's kind of ugly. Now, if you've never done logarithms before, here's how this works. What we can do is you can take the logarithm, we say, of both sides of the equation. And when you do that, that's like if you were punching it in your calculator, you'd hit the log button and then it would throw up a bracket. So you hit the log button, so you can do the log of 0.25 on this side. And when you take the logarithm of the right-hand side, the n as an exponent no longer becomes an exponent. That's why we're doing this logarithmic function, is because we're trying to solve for n. So effectively what happens is that n comes out of being an exponent and it's now in front of the expression n times the log of 0.5. Okay? So if you can follow that, this n that was up here, okay, this n here is now in front of a mathematical expression that is the logarithmic or the log base 10 function of 0.5, okay? Now, in your calculator, what your next step is, let's stay here, is your next step is to divide the right-hand side by the log of 0.5. Sorry, just the log of 0.5, not the log times 0.5. And then you do that on the other side as well. Okay? Now, that will then leave you with n. Oops. And this won't surprise you, but I'm just trying to show you in your calculator. So if you punch in log of 0.5, or sorry, log of 0.25, and divide that by the log of 0.5, okay, you get 2. Now, we just did that, so that means that the logarithmic, the number of half-lives, that's what we're finding, right? This smaller case n, the number of half-lives is 2. So this tells you, then you have to go back and say, well, wait, how much time elapsed for one half-life? That was the 5,000, whatever it was, 5,730. Is that what it was? Yeah, 5,730. Okay. So either from a graph, like so the skill is can you get it from a graph, or can you determine it either just being really practical, which most of the time you can get away with that. You can just say, oh wait, how many times did I cut this sample in half? If I did it twice or 3 times, 4 times you cut it in half, right? 5 times. So you cut it in half, then cut it in half, then cut it in half. Anyway, so if you do that on your calculator, you can determine if the number of half-lives and then work your way through. Okay, so I'll maybe just leave that there, but I do want you on your own, and I'll post the answers shortly. I do want you on your own to try number 2. It has 3 parts. Okay, A, B, and C. So I'd like you to see if you can do those. So the last part of chapter 16 is on fusion and fission. And this is such a fascinating area of energy because of its potential. And it also has a dark side to it. If you remember your social studies about the Second World War, there's fascinating history there in the development of the atomic bomb. Just quickly, famously, Albert Einstein had left Germany and become an American citizen. And he wrote a letter to, I think it was President Roosevelt at the time, and explaining to him the dangers of atomic weapons and how the Germans had the potential to develop an atomic weapon and that it could do massive devastation. Well, as a result of that letter, President Roosevelt started what was called the Manhattan Project. It was a top secret project with the focus of building atomic weapons. In the absence of Einstein, though, they didn't use him. They used a pile of other physicists. I think Niels Bohr got wrapped into it. Richard Feynman was a classic American physicist that did a lot of work in the Manhattan Project. Robert Oppenheimer was the lead scientist in the whole thing. Anyway, it's a really chilling and sobering yet fascinating piece of history. The Americans developed atomic weapons way before the Germans did. The Germans had started, but they were nowhere near where the Americans were. And we didn't know that, though, till the end of the war. It was really unnerving. It became this race to see who could develop the weapon first, because whoever did it first would win the war, and that's exactly what happened. Japan was very stubborn after Germany surrendered, and Japan kept fighting in the Pacific. And the Americans and the Allies never needed to use the atomic weapons on Germany. They were able to get Germany to surrender without that. But the Japanese were so stubborn that the Americans gave them a chance to surrender, but they didn't. And so they dropped the bombs. And it's just the energy released. It's chilling. But anyway, so I won't digress into that too much. But you need to know the difference between nuclear fusion, which is the combining of nuclei, and nuclear fission, which is the splitting. Okay, so I'm actually going to add this here. Nuclear fusion. Let's zoom in here. This is let me write it up here. This is where 2 small nuclei. Oops, sorry. I'm going to add that though. Yeah. Combine. And what you should know is they combine to a nuclei less than 60 nucleons. Okay, so fusion naturally happens less than 60 nucleons. Okay, and this is basically smaller than nickel and iron. Okay, if you remember, iron is the element that that everything wants to go towards. Okay, so there's really no fusion happens above iron. Okay, what's awesome about fusion is a couple of things. One is, though, let's maybe add that up here. Essentially there's no harmful products. Okay, there's some intermediate products that have some, but they quickly are they're quickly stabilized, and Fusion does not produce any radioactive waste. So the downside, though, for fusion is it requires huge amounts of input energy. Okay, I mean, if fusion is so great, we obviously haven't been able to do it because it's really tricky to do. It's easy to do in the hearts of stars because they're so massive, and the gravitational attraction is easily enough to cause fusion. Okay, but we have to input huge amounts of energy to do that. Uh, all you should see here in fusion, it can get really complicated. These are steps that show fusion in the sun. Okay, all you need to really see is at the end, if you're looking at the final reaction. See here, let's just blow it up really big. Um, Fusion is in the sun, obviously, is hydrogen that's fusing into helium. If I was to give you a reaction, which you will see shortly, and you have to say, hey, is this fission or is it fusion? All you do is you look at the reactants and you look at the products. Now, there's always some residual products here. Like, look at this. Here we got we have two positrons, two beta plus particles are produced. There's a couple of these are neutrinos, okay? And there's a bunch of photons produced, okay? So I call those residual products. Don't get distracted by those. What you're really looking for is any product that is bigger than any of the reactants. And look, we've got one here. We've got helium, which is, it's got 4 nucleons and 2 protons. That's definitely bigger than the reactant. Okay, in this case, it's hydrogen, 1,1H. So if you were to see this equation, you'd be like, is this fission or is it fusion? This is definitely fusion. We're making something bigger. Okay. Worth noting is anytime fusion happens, you also get a whole bunch of energy released. Okay. Now, all of these initial ones up here are, like intermediate steps. In the end, this is the grand total. So if you fuse four hydrogen atoms together and you make helium, you're going to release this much energy. Okay. So that may not seem like a lot, and it's not, but obviously if you do this with huge amounts of hydrogen, you can get a massive amount of energy released. And what's worth noting here is fusion. Let's maybe write it right here. It produces more energy per kilogram, or per unit of mass, per kilogram of reactant. Okay. So when I say that reactant, I'm talking about the hydrogen. Hydrogen is super light. It's like the lightest element on the in the universe. All you need is 4 of those, and you can make 26.71 MeV of energy. Okay. So hydrogen, and what's crazy is I was mentioning the atomic bombs. Those were fission bombs. Okay. Fission is way easier to do than fusion is, but since then we've developed hydrogen bombs. Okay, and hydrogen bombs are way more deadly than the fission bombs. As bad as the atomic bombs were in World War II, they don't hold a candle to the hydrogen bombs. Both Russia and the U.S. have tested hydrogen bombs, but there has never been a hydrogen bomb dropped on humans, on civilizations in war. And let's just keep our fingers crossed that never happens. That's what the whole Cold War was. I grew up during the Cold War, and I was kind of familiar with the fear and the intimidation of the Soviet Union versus the Allied forces, the United States. It was pretty real to me as a kid, and I even was a little terrorized by it in terms of wondering what I would do if a nuclear bomb was launched at my country. Anyway, so that is fusion, though. Fission. Fission is, and I should note this as well. All of the, like the conservation of nucleons and the conservation of charge applies. So all of the superscript numbers, okay, if there's, everything has to balance, okay? So it's just like we did with nuclear decay. Everything needs to balance, and you'll have to do that as you look at this here. So here's nuclear fission. So what we should say about fission, here, I guess I should just add this here. This is this happens when a nucleus that has greater than 120 nucleons. Okay, this is where that's kind of the benchmark. So fission doesn't just happen with anything. You have to have a pretty big element that's not stable because of its size, and then it will on its own split. Okay, so sorry, I got to finish this. A nucleus with greater than 120 nucleons splits into smaller nuclei. Okay, and again, this is all driven by stability. It's so fascinating. All the forces inside an atom are really what are dictating the fact that you can fuse or fission in the first place. Okay, so oh, you know what? Let's just add that before I go into the example. Yeah, there's no stable elements above 83. So I guess we should say that. Nothing's stable. Nothing is stable above 83. That's bismuth. Okay. Okay, if that helps you, or element number 83. And when we talk about fission, fission is easy to do. We do it all the time. In fact, we have nuclear reactors all over this planet that undergo fission. The famous one being Chernobyl. If you studied that, that's anyway. In our video that you watched earlier, it captured that history. Just a fascinating, again, a dark part of history, but a fascinating nonetheless. So in this case, though, products are unstable still, generally speaking. And so that's a bad thing about nuclear fusion, okay? That's what we call nuclear waste. Or radioactive waste, I guess we should say, because they keep producing radiation, okay? So, yeah, definite pros and cons with fusion and fission. Fusion is definitely way better. There's no question. If we can figure that out, and trust me, there's a fair number of engineering companies that are trying to figure that one out. Because if we can figure that out, we're going to have almost unlimited energy. But the irony is, there's already a fusion reactor that we could draw the energy from, and that's the sun. We just got to figure out how to make decent solar panels and store the energy, and then we've solved the energy crisis. Anyway, so let's end here. Fission. This is the reaction actually that I believe this is the reaction that happened in the nuclear bombs. Okay, you had to get refined uranium. You needed to get uranium-235, okay, which is a little bit unstable, but it'll stick together. And then you fire neutrons into it. So you can fire a uranium bullet into a uranium target inside the bomb. And it creates something called critical mass. And when that happens, basically, all of the uranium atoms destabilize almost at the same time. So almost every uranium atom is getting hit with a neutron like this. Okay, with a neutron coming in. Okay, that hits a U-235 and it makes temporarily U-236, which is ridiculously unstable. Like it'll only stay together for milliseconds or something like that. And then that just goes, okay, that breaks up. And it forms krypton and barium is one possibility. There's a couple other possibilities. What's just insane here is it creates 3 more neutrons, okay, and then those 3 neutrons go off and hit some more uranium atoms. So that's what a chain reaction is. And if you can kind of accelerate that, which is what happened in Chernobyl, the reaction got out of control. Okay, uranium atoms were starting to decay and they were throwing out neutrons. They were hitting other uranium atoms and they shut off their control rods. Anyway, pulled them out or something, and the reaction just got out of control and they had a meltdown. It was brutal, just brutal. So the point is, it releases a ton of energy. In this case, 200 MeV, which is way more if you'll compare that to this 26.71. Okay, so this releases a lot more energy, but it requires really large atoms to do it. So this is kind of the finer understanding of the difference between fission and fusion. And I'll maybe note it over here, okay? Fusion, or sorry, let's say fission. Fission releases less energy per kilogram than fusion. Okay, and the reason for that is, look, you need a massive particle. You need U-235, okay? It's a really heavy element. Okay, 235 nucleons, 92 of those are protons, obviously. But you need a really big element to start with, and then that breaks up. So per kilogram of mass, you actually get much less energy released. So fission is easily attractive because it's relatively easy to do. So the last thing I want you to see about this is the arithmetic. So the total numbers, the nucleon numbers have to be conserved. So that would be, that's the top number. So you have 1 plus 235. See, so that creates, and here's this compound nucleus, U-236. So you see that? So all the numbers are conserved, setting you up to, in fact, this diagram is incomplete because it shows that the U-236, which is unstable, splits into barium and something else. Well, it makes barium and it makes three neutrons, okay? So, but the neutrons all have, so anyway, what you should be able to do here, which isn't too bad, just using arithmetic, we start with U-236 in the intermediate step. So that means there's 92 protons. Well, that means then that there has to be 92 protons at the end because we didn't lose any protons, okay? So 50, we'd have to go basically 92, minus 56. And because there's 56 neutrons up here. So that would give you the 56 neutrons, or no, 56. No, sorry. I'm overthinking this here. Yeah, we get 36 protons. So this element down here would have 36 protons. Some of you can see from the equation, but if you're not sure, you would do the arithmetic. You'd look at your periodic table and you'd look up 36 and go, that's krypton. Woohoo. So, but it's krypton, and what isotope of krypton is it? Well, then we'd have to look at the top number, which is the conservation of nucleons, 236 minus 141 minus 3, okay, because you got 3 neutrons as well. So doing all of that would give you 92. Ooh, that's interesting because that's the same as uranium, okay? So anyway, I'm just showing you that you're going to have to do some of that arithmetic. That's already confirmed, though. This equation was already balanced, if you guys can see that, okay? So 1 neutron plus uranium-235, it went to krypton, barium, and 3 neutrons. And all those numbers balance out, okay? Or sorry, they all equal each other. So that's all I wanted to add about fission and fusion. So if you understand those principles, there'll definitely be some theory questions. See those in the upcoming test. So I'm going to post a chapter 16 homework test. It's going to work the same as the chapter 15 homework test. I'll give you a day or so to kind of get through all this stuff, or a couple of days if you need, before I start chapter 17. Chapter 17 is also a little bit small, so it won't take us too long to get through that, and then we'll kind of review everything. So anyway, look for the posts and for some answers coming, but keep up the good work, you guys.